Okay, so what does that mean about we've done the interior angle sum. What does that mean about the exterior angle sum? So we're going to explore this a little bit in class, but what I want us to start with is an equilateral triangle. So think about an equilateral triangle. An equilateral triangle, I like to call it the perfect triangle. It's got all three sides are congruent and all three angles are congruent. And what did we just say? We said that the interior angle sum of a triangle is 180 degrees. So if all three of these angles are congruent, we know from a previous chapter that the equilateral triangle has three 60-degree angles. Those are interior angles, okay? So let's start looking at its exterior angles to come up with this number without just me giving you the answer, okay? So those are our interior angles, and together the interior angle is going to make a linear pair with our exterior angle, and there are three interior and three exterior angles. So if those make a linear pair, that means that those add up to 180 degrees together. So what is 180 minus the 60 I've spent? That gives me 120 degrees for each of these exterior angles. So what is 120 times 3? 120 times 3 gives me an exterior angle sum for this triangle of 360 degrees. So we'll look at a triangle in a minute that is not perfect like that. We'll come up with a word for that in a second. But now I want to look at what is a perfect quadrilateral. We know that the perfect quadrilateral, where all of the sides match and all of the angles match, is called a square. Interior angle sum, of course, is 360, and those are all 90-degree angles. So when I extend these lines, and I use some auxiliary lines here, I extend these lines to create these exterior angles, these are still going to add up to 180 degrees. So what are these green angles going to be? There's only 180 minus 90 just gives me 90 degrees left for all four of these exterior angles. So what is 90 times 4? That is also going to give me an exterior angle sum of 360. And so in class, many of you started to catch on to, well, are they always going to be like that? So this is where we use GeoGebra. And we looked at this page right here, and I had different students calculating these things. So some students tackled the triangle. Now you can make this triangle look like whatever you want. You can make it as wonky as you want. You can make it scalene, you can make it isosceles, you can make it equilateral. But no matter what, we discovered that if the number of sides is 3, the sum of the exterior angles was 360. So that's for all triangles, okay? All right, if the number of sides was 4, no matter how we change this, no matter how we move this around, the number of sides was 4, our exterior angle sum was still 360. Same was true for a pentagon, any pentagon, and then same was true for a hexagon. We even backed it up and looked at this visual, which gives us, I believe that this is an 8-sided figure, 1, 2, 3, 4, 5, 6, 7, 8. And we said that as you make the sides smaller and smaller and smaller and smaller, these exterior angles get closer until the sides fully disappear and what is formed? A perfect circle. So even though all of these angles are different, when you put them all together, it forms a perfect circle, and we know that a perfect circle is 360 degrees. So this part is easy. We get to copy 360 all the way down, 360 all the way down. So for any polygon, any number of sides, the exterior angle sum is always going to be 360 degrees, no matter what, okay? So I could go all the way down to a 100-gon, and it still would have an exterior angle sum of 360, okay? All right, so on the back, we just talked through these things briefly, and we're going to do more actual math work with this tomorrow. But those things that we called perfect earlier are actually called regular polygons, okay? We know that it's called equilateral if all of the sides are congruent. Y'all have seen this before. If all of the sides are congruent, it's just equilateral. So what that might mean is that this angle is acute and this angle is obtuse, so those are different. Those don't match. If it's just equiangular, that's where only the angles match. So maybe the side lengths are different. So you can kind of tell the way that this is drawn in the picture that maybe this side is longer than this side. So the sides are different, but the angles are congruent. So what is it called when it's regular? It is regular if it's both equilateral and equiangular. So if it's both of these things, if all of the angles match and all of the sides match, so I'm going to get the yellow parts from the equilateral, I'm going to get the blue parts from the equiangular, all the angles match each other and all the sides match each other, that's what we call a regular polygon. So all of these I have in these pictures, equilateral triangle, square, regular pentagon, regular hexagon, regular heptagon, and so on, those are all of our regular shapes where all of the sides match and all of the angles match, okay? So these formulas up here work for any kind of polygon, whether it's regular or irregular. That gives me the total sum of the interior and total sum of the exterior. But let's look at what happens, and let's talk about what happens when they are regular. If we have a regular polygon, the measure of each interior angle of a regular n-gon is what? So I actually want to back this up to this picture right here. We know that this is regular. So what is the interior angle sum? You'd say 6 minus 2 times 180. 6 minus 2 gives me 4 of those triangles times 180 gives me a sum of 720. That's if it was regular or not. But let's say I told you, okay, you and some of your friends won $720 and you're going to split it evenly. Well, what is each person going to get? What is each of these amounts going to be if it's even and if it's fair? You're going to take 720 and you're going to divide that total by 6 because there are 6 of you sharing it. And 720 divided by 6 should give me, I think it's 120, but let me see. 720 divided by 6 gives me 120 degrees for each of these. So 120, 120, 120. Every single angle in this regular, since they're the same, the interior of this regular hexagon is going to give me 120 degrees. So that's where that process comes from, and that's where this formula comes from. For a regular polygon, the measure of each interior angle, not the total, but the measure of each, is going to be n minus 2 times 180. That gives me my total sum. N minus 2 times 180 divided by n, where n is going to be the number of sides. So n equals the number of sides. So we just did that with a hexagon. So we can actually go ahead and copy that answer next to it. Find the measure of an interior angle in a regular hexagon. That's what I just did here, but just keyword, it had to say regular. We wouldn't be able to do that if it just said hexagon, because they don't always match. They only match if it's a regular polygon. So let's do that again, that same process, but for a nonagon. So how do we find the total? We do 9 minus 2 is 7, times 180 gives me the number of triangles. So 7 times 180 gives me 1260. And we want to take that and we want to divide by the total number of exterior angles, which is going to be 9. So what is 1260 divided by 9 interior angles? That would be 140 degrees each. 140 would be my answer for the measure of each interior angle. So there would be 9 of them, and they'd be 140 degrees each since it's regular. So this only works for regular polygons. That's interior angles of regular polygons. Now let's look at exterior angles of regular polygons. What do exterior angles measure? We know that the sum is always, always, always 360. So if I said, what do angle 1, 2, 3, 4, and 5 add up to? You would say, no matter what, 360 degrees. That would be my total. That's not what it asked, but we're going to come back to that in a second. The same would be true of these. What would angle 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 add up to? It would still be 360. I could put 1,000 angles on there, and it would still be a sum of 360. But if it's regular and I want to find the measure of each exterior angle, that means just take the number of exterior angles you have, which matches the number of sides, and just divide by that. So 360 divided by n, where n is the number of sides, it will also be the number of interior angles and the number of exterior angles. So if 360 is my sum of all of these, what is just the measure of angle 1? Well, we know it's going to be the same as 2 and 3 and 4 and 5 because these are regular. So the interior angles are all the same, and so the exterior angles are all the same. So I'm going to divide that by 5 exterior angles. So what is 360 divided by 5? It should be 72. So what is angle 1 in this picture? 72 degrees. But what is angle 2? Also 72 degrees. What is angle 3? Also 72 degrees. It is 72 degrees for every single exterior angle. And what is 72 times 5? That is 360 degrees. So that's just the measure of each one. Same thing here, and I did ask this in every class. Should the measure of angle 7 be bigger or smaller than 72 degrees from my previous? Well, because we're going to an octagon, the number of exterior angles is increasing, which means my denominator is increasing. And that means another way to say that is I'm splitting the money, the same amount, the same total. It's still 360, but I'm splitting it between 8 friends instead of just 5. So that number should go down. You're getting less money when you split up that money. So what is 360 divided by 8? It is going to give me 45 degrees. So what is the measure of angle 7? It's 45. What is the measure of angle 2? 45. Every single one of these would be 45, and they would have a sum of 360 degrees. So we will do more with that math tomorrow. This was really just an introduction to these shapes and where these formulas come from. I wanted y'all to understand the concepts before we get into the procedures. So I hope you're having a wonderful day.